So now we'll look into Heisenberg ideas about incompatible observables. So you can have two dynamical to canonical conjugate variables. Okay, they are specified by some other properties. So they are canonical conjugate variables. And these two canonical conjugate variables, they cannot be measured simultaneously and accurately. So this is the definition for uncertainty principle. There is an uncertainty in the measurement of x. There is uncertainty in the measurement of momentum. It is not written as x and p. It is written as del x and del px. So look at the expression. Del x stands for spread, the range. It is not x, del x. In mathematics, we can say this is standard deviation. How many measurements we can, again we will have standard deviation. You just take number of measurements, again we will have, there will be a spread. So it is not specifically mentioned that it is not x, it is del x. So del x and del px is greater than or equal to h bar. So this is the uncertainty relation. It says that any two canonical conjugate variables cannot be measured simultaneously at the same time. We can say that x, I can measure x and I can measure p different time. No, it is not like that. Simultaneously you can't measure. For example, just take classical objects. Suppose if I throw this one, okay, if I have initial velocity and mass, and if I throw this one, and I know where it's going to fall, I know the height and I know the place where it's going to fall, final velocity, I'll come to know all those things using equations of motion, Newton's equations of motion. Okay, so at the same time I can find out the position and the velocity. But in quantum state it is not possible because it's associated with the wave. So there will be a spread. So it cannot be measured simultaneously and accurately in quantum mechanics. Okay. Now is it connected with some measurement devices? We don't have enough equipments. No, it is not like that. It is like that. Do you think that it is connected with some equipments? We don't have enough equipments to measure this one. No, it is inherent property. It is nature. Nature for any quantum state, it's a nature. It's inherent property of any quantum state. Okay, del x and del px greater than or equal to h bar. So it is not. Do you think that it is not connected always with Cartesian coordinates? No. We can have a polar radial distance del r and del pr. They are all canonical conjugate variables, del r and del pr. Okay, r is the distance from the radius, and pr is the component of the momentum. Okay, so those two are canonical conjugate variables. They are canonical conjugate variables. What about x with py? They are not canonical conjugate variables. X with py, x with pz, they are not canonical conjugate variables. X with px, y with py, they are canonical conjugate variables. Okay, so they are not canonical conjugate variables, dynamic variables. So we can't measure them. We can measure them simultaneously. Here we can't measure them. Okay, we can measure them simultaneously. So compatible observables, incompatible observables. Okay. Now we'll see first from de Broglie's relation how the wave packet is defined. Okay, how del x is proposed. We'll think it out. Suppose if we consider this wave, so it goes from minus to plus infinity. Okay, so this wavelength is exactly, I know the wavelength, distance between any two crests or any troughs. So lambda equal to h by p. If lambda is known, lambda is well known. Correct? This is ordinary wavelength. See, it is uniform wave. So lambda is known. Distance between these two. So lambda is known. Correct? If lambda is known, momentum also is known. What is the position of the particle? Momentum is known now. So I would like to find out the position now. What is the position of the particle? Position of the particle will be always with the highest probability. Okay, so maximum amplitude. So position of the particle is somewhere here, somewhere here, somewhere here. So negative cannot be done. So somewhere in the positive direction. Okay. So that's why we have taken mod square. Correct. So negative probability does not exist. So that's why we used to take mod. So now these probabilities, you look at this one, it goes from minus into plus infinity. X, you can't define particular in the position x will be there, we can't say. It goes from minus into plus infinity. Momentum is well known. The position of the particle is doubt. So where the particle is located, because it goes from minus into plus infinity, it can exist here, it can exist at which place I am going to take, that we do not know. So position is ill-defined, position is poorly defined, whereas momentum is clearly defined. Okay, if I want to define out of these two canonical conjugate variables, if I want to define one thing, I cannot define another thing. If I want to define another thing, I cannot define one more thing. So there will be uncertainty. The more accurate we want to measure this one, there will be less accurate on measuring this one. So we can't measure simultaneously, okay, for any normal wavelength. Suppose if we consider the wave packet, of course all quantum states, quantum particles are represented in terms of wave packet. So wave packet in which waves will interfere inside. So we know already this one, okay. So superposition of all waves which exist inside. So if you have constructive interference where the particle is present. Here it is a destructive interference where the particle is absent. So we know already. Okay, so this is called a wave packet. And this is the group velocity, this is the phase velocity. Group velocity is nothing but the envelope. The envelope is nothing but group velocity. Group velocity is nothing but the particle velocity. Particle velocity of quantum state. So here you just look at the wave packet. Here position and momentum both are ill-defined, both are poorly defined. So we can't find out lambda, exact lambda here. Here we can find out the lambda. So here look at the wave. So we can't find out lambda. Correct? What is the position? The highest probability it can exist here. Here it is nearby. So again it is both are ill-defined. So that's why they have constructed wave packet exactly like this. Okay, both are ill-defined. Both are poorly defined. Okay. Now we will look at this picture, how a wave packet is being built. We consider this wave, it's a uniform wave. We will consider, I said just now, wave packet which consists of different wavelengths, I said, correct? Superposition of different wavelengths. You just consider another wave. So this is in the brown color and this is the green color. Okay. So now we are going to superpose these two. So like that we are going to superpose many waves. Now if all the waves they merge together in this position, superposition, they see, look at this one, they merged. So where the particle is present, so here where the particle is present, constructive interference. So here is just opposite direction. So crust is here, trough is here for another wave. So just opposite direction. So here there will be no particle. So destructive interference. So here constructive interference. So this is how a wave packet is being built. So we have a wave packet exactly like this. Okay. So one wave packet, the spread is nothing but your del x. So this is what the superposition, the resultant wave is given. So this is the wave packet. So we have a destructive interference on both sides. We have a constructive interference at the center. Okay. Superposition of many waves. So uncertain in wavelength, then uncertain in position. Okay. So this is a del x. Now these canonical conjugate variables which Heisenberg taught about Fourier transform. So Fourier transform is a technique we know already. From you can use an operator or any function changing from one domain to another domain, from time domain to frequency domain. If you want to change from frequency domain any signal, if you want to have any signal from one domain to, you can go with another domain. For example, frequency domain to time domain or time domain to frequency domain. So this is what the Fourier transform is. Okay. Similarly, he took these two variables x and p, both are Fourier transform. Okay. So you have wave packet like this, for example. So wave packet del x. Here the Fourier transform is nothing but your position space and momentum space, k space. This is coordinate space, ordinary position space. This will be coordinate space. So the Fourier transform of position space for any packet will be exactly like an arrow. See, this is broad, somewhat broad. This is narrow. The Fourier transform of broad one will be narrow. Fourier transform of narrow wave will be broad. So this is vice versa. Okay. For this is the bell-shaped one. Bell-shaped function del k. So del x and del k. If you want to approach del x very narrow, del k will be broader. When del x will be very broader, then del k will be very narrow. Okay, we are going to interpret, we can get the uncertainty principle from Fourier transform. Let us see how it works. So experimentally theoretically we can say that using standard deviation, del k is greater than or equal to 1 by del x. So mathematical step says that del k greater than or equal to 1 by del x. In fact, this is del x del p greater than or equal to h bar is the experimental fact. So in the year 1925, scientists conducted this experiment. Okay. So now del k is greater than or equal to 1 by del x. We know from standard mathematical methods we know. Now just look at this expression del p equals del h by lambda. Okay, lambda equal to h by p, we know already, de Broglie's hypothesis. So del p equals del h by lambda, and we know that k equal to 2 pi by lambda. So your del k will be 2 pi by del lambda, correct? So you can substitute in this expression. So you have instead of lambda you substitute 2 pi by k. Okay, so del lambda will be 2 pi by del k. So you have h is there, you have 2 pi divided by del k, that will go del k. Okay, h by 2 pi, that will give you h bar. So h bar del k. So therefore del k equals del p by h bar, correct? So you will have del k equals del p by h bar. You have del k equals del p by h bar. You substitute in this expression, you will get del x del p greater than or equal to h bar. Simple. This is one idea. Okay. Not only for del x and del p, del e del t, that also pair, another pair. Del e del t, another pair. So for example, e equals p square by 2m. Your del e will be, you just differentiate, that will give you 2p del p by 2m. 2 to get cancelled, you have p del p divided by m. P equals mb del p by m. Correct? mm get cancelled. You have v equals del x by del t. Okay. So therefore del e equals del x del p by del t. Cross multiplying will give you del x del p greater than or equal to h bar. Okay. So this is the way that uncertainty principle with two pairs del e del t and del x p have been derived. So this is the wave packet description, and we have used the technique Fourier transform. Okay. And of course that 1 by 2, in some other book we can find that 1 by 2. The minimum uncertainty will occur using standard deviation is 1 by 2. So h bar by 2. Now we will go with another definition to get del x del p x greater than or equal to h bar. So now we know that x is a displacement for any wave, then we can say that del x equal to n lambda. Okay. So del x equals integral multiple of lambda. So del x equal to n lambda, which is equal to n, the de Broglie's hypothesis, h by p. Also from waves, lambda equals to n del lambda, number of times. So we know this. So n equals lambda divided by del p. So lambda divided by del p, that will give you p divided by del p, using that relation. So del x equals, instead of n you can substitute p by del p. So p by del p, correct? P by del p, h by p. Okay, p gets cancelled, you have h divided by del p. So del x equals h divided by del p. So del x del p x is equal to h bar. Okay, h or h bar by 2. Okay, it's equal. Equal means minimum uncertainty. So there will be a minimum uncertainty. And look at the graph, del x del p. So both the products. Okay, and you will get a rectangular hyperbola. So if you draw the graph between del x and del p, you will have a rectangular hyperbola. What does it say? It says that when del x is very large, del p is very, very small. When del x is very, very small, del p is large. Okay, and also minimum uncertainty will occur somewhere here at this point, del p del x. Okay, suppose if I want to reduce del x, I am going to squeeze it, del x almost tends to 0, then del p will become infinite. This relation says. Okay, so since the waves are irregular in the wave packet, we can write del x del p x greater than or equal to h bar. So we have taken from the standard deviation. Okay, del x, as I said, del x is a spread, standard deviation. This is a variance, square root of variance. So your del x will be variance minus square root of the variance. So we have taken only from the standard deviation. So there is no sharp value as I said earlier. So it is connected always, standard deviation connected with probability distribution. Psi is connected with the probability amplitude. This probability amplitude can be derived from Schrödinger wave equation. So we have to use Schrödinger wave equation to get the wave function, value of wave function. Okay, so this is your uncertainty relation. Okay, so we have derived uncertainty relations in 3 different ways. Okay, then we will go for one problem, last problem. Use the uncertainty principle to estimate the ground state radius of hydrogen atom and the energy of the hydrogen atom. So we are going to use uncertainty relation. We are going to calculate the ground state radius, the radius of the ground state of hydrogen atom. Second one is energy. We know already these two values we know already. Okay, we discussed or we studied earlier in +2 itself. Okay, in the college 3rd year itself. We know already the value. The value of ground state radius will be 0.53 angstrom. The value of energy will be minus 13.6 electron volt. We know already this value. Okay, we will see. Now we are going to use uncertainty relation. Uncertainty relation is del x del p greater than or equal to h bar. Correct? Correct. So for the time being I can write this Rp approximately equal to h bar. Okay, so P equals h bar by R. So energy expression for any ground state energy expression, that will give you kinetic energy plus potential energy. Potential energy will be always negative, so that's why it's negative sign. Okay, so you have kinetic energy plus potential energy. So instead of P we can substitute h bar by R. So h bar square divided by R minus E square by 4 pi epsilon naught R. So ground state radius of hydrogen atom is asked for the first part. You just minimize with respect to R, minimize the energy with respect to R equal to 0. That will give you radius R. You just differentiate. Okay, you just differentiate with respect to R. We are going to differentiate with respect to R. So you will get 1 by R square. Differentiating, that will give you minus 2 by R naught, R cube. Okay, so for timing we will go for R equals R naught, which says that radius of the first radius of the ground state. So you have minus h bar square divided by me R naught cube plus the next one will be, you are going to differentiate with respect to 1 R. So 1 by R will be minus 1 by R square. So you have minus plus, that will give you plus E square by 4 pi epsilon naught R naught square. You pull this term to right hand side. So minus will get cancelled, and you have R naught cube and R naught squared. Both will cancel, you will get only R naught. So expression for R naught will be 4 pi epsilon naught h bar square divided by me E square. Correct? You just substitute all the values, you will get 0.53 angstrom. Okay, so that will be your assignment. So epsilon naught 8.85 10 power minus 12. Okay, SI unit. Your h bar equals h bar equals h divided by 2 pi. The value of h will be 6.626 10 power minus 34 Js. And m, mass of the electron, 9.1 10 power minus 31 kg. And your E will be 1.6 10 power minus 19 coulomb. So you have all the values. Okay, you will get in terms of meter. You just convert into angstrom. You will get 0.53 angstrom. So this is the Bohr radius. 0.53 angstrom is the Bohr radius for the hydrogen atom. Okay, so this is a distance between electron and proton. It's a mean distance. Okay, and second one is energy of the hydrogen atom. Energy of the hydrogen atom, you have already got the value of R naught. You substitute here. Value of R naught will get. So you have h bar square divided by 2me instead of R naught. So R naught squared minus E squared by 4 by epsilon R naught. You substitute all the values, you will get in terms of joules. Divide by 1.6 10 power minus 19, you will get in terms of electron volt. Okay, 1 electron volt equal to 1.6 10 power minus 19 joules. Okay, so you will have in terms of joules. So just divide this one by 1.6 10 power minus 19, that will give you in terms of electron volts. So this is minus 13.6 electron volt. It's a bound state. so minus exists. Okay, so this is the energy of the hydrogen atom. So we will stop today, and these two concepts are very important in quantum mechanics. So thank you, students. We will see you in the next class.